1977, Les Tournois de France, Brazil versus France, in a warm up match for the World Cup the whole planet is about to watch. Roberto Carlos plants the ball 35 meters out. Everyone leans one way, he blasts it another. So far wide, the ball boy behind the goal flinches and ducks. And then it comes back. The ball bends in mid-air, swerves around the wall, and snaps into the top corner. The keeper never moves. For 13 years, people argued skill of the century or a total fluke. Today, we settle it with physics. Here's what should happen: you kick a ball, gravity pulls it down, and it flies in a smooth arc, a parabola, no surprises. But Carlos' ball didn't just arc down, it curved sideways. Hard, late, like it changed its mind midway. Nothing touched it. No wind gust, no second player, no bounce off. The ball flew a clean, curving path through empty air. So, what reached out and shoved that ball back into the target? The answer is one thing. The one thing only: spin. Watch the ball spin as it flies. One side spins into the oncoming air, the other side spins away from it. Air racing past the with the spin side gets dragged along and speeds up. On the other side, the spin fights the air and it slows down. Fast air means low pressure, slow air means high pressure. High pressure shoves towards low, so the whole ball gets pushed sideways, the way it's spinning. That sideways shove has a name: the Magnus effect. You don't need heavy math to feel this. The sideways force grows with three things: how fast the ball flies, how fast it spins, and the density of the air. Speed, spin, air. Crank up any one of them, and the curve gets sharper. Carlos maxed out all three, a rocket of a strike with a savage side spin. That's why his ball turned when a gentle pass never would. This isn't new. In 1672, a young Isaac Newton watched tennis players at Cambridge and noticed the spinning ball curved. One side, he wrote, beats the air more violently than the other. 2 centuries later, in 1852, German physicist Heinrich Gustav Magnus put it to the test, spinning a brass cylinder in a stream of air and measuring the sideways push directly. Newton spotted it on a tennis court. Magnus proved it in a lab. Carlos, he just weaponized it. Let's put numbers on that strike. The ball left his boot nearly 130 kilometers an hour, spinning around 10 times every second. And that speed, the air can barely bend it. But drag is relentless. The ball slows down while the spin keeps going. And a slower ball with the same spin will curve harder. So the turn isn't strongest at the start, when the ball is screaming through the air. It's strongest near the end, right as the ball arrives at the goal, and right when the keeper has already committed. That's the cruel genius of it. The ball looks like it's missing until the exact moment it can be saved. In 2010, the four French physicists finally did the full math. Their paper had a beautiful name: the spinning ball spiral. Their punchline: for a short free kick, 20 meters out, you just get a smooth curve. But go far enough past 40 meters, and the trajectory stops being a simple bend. It coils into a spiral. Carlos struck from 35. He was standing in exactly the zone where a curve becomes a spiral, not a fluke. A man who found the edge of the physics. So the impossible goal was never impossible. Spin drags the air, pressure shoves the ball, drag saves the sharpest turn for last. And it's everywhere once you know the shape. That same sideways shove swings a cricket ball, lifts a golf drive down the far way, dips a tennis topspin inside the line, and floats a curveball past a swinging batter. Newton saw